Looks like class can start. Welcome back, everyone. Well, I have a couple announcements to get going with right away. We got through our first exam week and, oh, where am I? Let me scroll to the right spot. And I've graded some of the exams, but I haven't graded the whole set, unfortunately. However, once all of the exams are graded, there's going to be a new document right here, which will contain the solutions to the exams. And also post some summary statistics right down below, just summarizing how it went for everyone in the class. But for folks curious, this section right here, the online section, primarily students in Pocatello, we're working through the Pocatello Testing Center. And it's going to take them a little bit more time to get all the exams scanned up and emailed back to me. The moment they have them sent to me, I'm just going to start grading them as soon as I can throughout the work week. And I should have them all graded by Friday at the very latest. Let's hope it doesn't take too long. But I thank everyone for their patience with that. That's something that's kind of new to me, dealing with the extra backlog of having those exams run through the Pocatello Testing Center. Any questions at the moment, folks, about any of those announcements? Okay, well, the other announcement is, aside from exams, I got quite a bit of emails over the weekend. Well, not a ton, but more than normal, reminding me that Valentine's Day is this Wednesday, and we're also a night class. So I decided to, why not? It never hurts to ask, and there are several people asking about it. We won't hold a formal class on Wednesday due to us being a night class and it being Valentine's Day. Instead, we're going to think of it as kind of a catch-up day. I'm still going to have office hours, so I'll still be available at the normal times and places. And if you're working on that night, you can definitely hit your WebAssign Ask the Teacher button as much as you like, stuff like that. I'll be happy to help out as well. So we won't have an official class. So for quiz 4, we'll have to push the due date. I won't be able to collect it on Wednesday officially, but you can always hand them in virtually if you'd like. If you'd like to hand in a hard copy, the due date's been pushed to the 19th right here to make a little bit more sense. Let me think about that though. That's a problem as well. Let me take a look here. We have also President's Day, the 19th, so I need to push that even further. Let's maybe make it the 21st, something like that. I might move this one just because I don't like collecting two things on one single day. But I'll make sure that you can hand these in person at a normal time. You're not going to be docked for credit. That's essentially what's going to happen with the due date on that one. Any questions about that so far, folks? Yeah, I just turned it over just this morning. Yeah, sorry for that weird change. Well, I think we're about ready to get started then, folks. I'm going to send a reminder out as well. I'll send a mass email to the class that, don't forget, we decide to cancel Wednesday's class, essentially, make it a catch-up day. So that's going to happen on the forum post up here. I've been starting to use this. It's kind of a convenient place. And so you can see those kinds of historical comments as well posted here. Well, aside from all that stuff, looks like we're about ready to get going. We're in a kind of exciting portion of the course. It's section 3.3. We're looking at how to differentiate a lot faster than using the limit definition. Limit definitions will come back once we turn over to integration. We have to start with what are the limit definitions for that. At the moment, this is pretty much what we're doing. Let's run through these. We have a derivative of a constant as a formula. So anything that comes up as a constant, say, for an additional example, if y equals 15, you can say immediately dy dx is 0, or you can write it out this way. Y prime is saying the derivative, but it's a constant, so you just get 0 in that case. Next, if you have a power function, this one's pretty nice and self-explanatory. The power 7 comes down, and your new power is 6. So that's a fast formula. Then we have a couple other formulas that allow us to manipulate with a constant, as well as a sum or a difference here to here. And let's do maybe one additional example here tying that together. If you're differentiating a polynomial, this is pretty much how it goes down each and every time. For another version, let's say y equals 16x power negative 2 plus 13x power negative 1. This one just looks funny, right? It's actually not a polynomial any longer due to the exponents being negative. Polynomials need to have non-negative exponents going on with them, but we can still just differentiate this as normal. We use this pretty much verbatim. d by dx of x power n is always n times x power n minus 1. Let me put a little partition there. So if we see a function in this format and we need to differentiate, it doesn't matter if it's positive, negative. In fact, this -1 could be negative 1.1. The pattern is always the same. You can say dy dx is -2 comes down and multiplies, so that's a -32. The new power of x is 1 less, so always subtract 1 no matter what. That means the new power is a -3. And we have a formula that says if there's a plus in the middle, no worries, just break up the derivative. We differentiate this next. -1 comes down, so it's a -13. New power on x is 1 less, so now it's power -2. We can keep on repeatedly differentiating these things, getting the powers smaller and smaller as we go, or larger negative rather. But that's the pattern so far on this to this. Well, any questions, folks, so far with the rundown of these two? Okay, so those were our nice formulas. And they all go together really kind of well, I'd say. But then we mentioned that we have to be pretty careful whenever you see these types of formulas. The derivative of exponential functions always looks a little bit different because x is now a power. It's no longer the base like in the prior settings. This derivative just gets you back at 5x. But the danger here is more when you see these kinds of problems. This one was a constant, so it goes to 0. There is no power rule for this one. This one does involve the power rule because x is the base and the power is a constant. And this one, well, it's an exponential function, so the derivative goes like this. And it only works for base e specifically. We need a brand new formula if it's like base 5 to power x, for example. But for the moment, these are the formulas that they gave us for section 3.3. So what we'll do now is just practice using them. Any other questions so far, folks, with the rundown of those formulas? This one right here, yes, in the middle is the power rule. That's actually a pretty good thing to indicate here. This one is the constant rule. The one in the middle is the power rule for the power function, and the one on the far right is natural exponent rule. We'll see why it's called natural when we see the other rules for those exponential functions. They get a little bit more involved, but this is a natural exponent in the sense that the derivative on this one is as easy as possible. Nothing changes. Other questions so far? Okay, now let's start putting this to use. Example 1, let's put this on the new page. It's something we have solved before. We did this in section 3.2. Let's take a look at how that solution went. In 3.2, it said we were just getting used to, actually this must have been 3.1. Yeah, way back. So section 3.1, we were defining the derivative. The derivative is just the slope of the tangent line. And we decided to practice with it immediately on this problem right here. We want to find the equation of the tangent line to that curve at the point 1, 2. You know, it wasn't too bad unless you look on the right-hand side here. A bit of algebra did have to happen. But we got through the limit statement. We found the slope. Then this right here gave us the tangent line equation. We're trying to get -3x plus 5. So let's try it all over again with our new formulas. I did this example 1 as a redo because it's sometimes a good idea to show, even if they're asking you to do the tangent line, you're still not using those old methods. You want to use the brand new methods to power through this. So here's how it should go for this kind of situation. First thing we do is, if you have a function y, calculate dy dx, or y prime if you prefer. I'll go with the Leibniz notation, dy dx. First we differentiate x squared, 2 comes down. And when the new power of x is just a 1, we usually just leave it as x. So that settles off that first portion. The next portion is -5 times x. Whenever you deal with that, you just get -5. Nothing special happens there. And that's because that's a linear function with slope -5. It's immediately its derivative. Or another way to think about it is you're differentiating with respect to x, negative 5x. You can think of it from this point of view. So this is the explanation, but from here to here, this is a very, very worthy shortcut. People will typically always do it this way each time. But here's how it goes. There's really a power of 1 right there. This negative 5 can also move outside as a constant. Then we're differentiating negative 5 times the derivative with respect to x of x power 1. We know our format is 1 comes down, it's going to multiply the negative 5. New power of x is 1 less, so now it's power 0. But then down here, x to the power of 0 is literally a 1, and so we get just negative 5. It's negative 5 times 1 essentially. So if you see the power of x is 1, the punchline is it just differentiates by taking away x and pulling in the coefficient. Does that make sense to folks on the explanation of why it should go that way? Okay, then same kind of idea on this one. You could use a power rule to show how this could go. You just put a power 0 here. 0 would come down, wipe out the positive 6. And even if the new power is negative 1, you have 0 times x power negative 1. But probably the better thought if it's just a constant, derivative of a constant is immediately 0. So we just don't even write in anything at that stage typically. So that's the derivative as fast as possible. I think it took us 5 or 7 minutes last time we did it. That's not exactly what we want, but it's a good start. Next thing we're going to do is take that value right there. Actually, I want a slightly different color. Let's take this value right here. If we plug that into the derivative, we'll get our slope. So let's say here, m for slope is going to be the derivative, dy dx, but it's evaluated. It has to be evaluated at the first coordinate that was provided. Already, that's kind of an interesting confusion. If you're given a whole point, 1, 2, you're always plugging in the very first point into your derivative. Let me do that slightly better. Let's say specifically which variable. X equals 1. That's quite a bit of notation. It's saying take the derivative of y with respect to x, plug in 1, and it will output the slope that we're looking for. So here's how it goes next. It's 2 times 1 minus 5. So this is pretty much just 2 minus 5 for a slope of negative 3. Now that we have that, we're just going to use the full point and build up the equation. I'd say this is pretty much the punchline though. If this was a real question on exam 2, I think most of your credit is knowing you need to calculate the derivative and knowing you need to plug in 1 into the derivative to get the right slope of negative 3. I would consider that to be like 3/4 of the credit or something about like that. Well, next step is you can build the equation of your line using any format you'd like. Some people use point slope form, y equals mx plus b. I typically go this way just because the book does it as well, so it feels more standard when you're reading the book. This one is the the point slope form. Y minus y1 equals m times x minus x1. But again, if you like to go from here, it also works, and you don't have to change your methods. Well, we can get our x1. It was provided in the coordinate, and so is y1. It's the second coordinate right here. So all we're doing now is just plugging in our work and solving for y. So it reads y minus y1. Y1 is that second coordinate for a 2. Equals the slope m. That's where we brought in the derivative and worked with it. And it settled in as a negative 3, so it should go here. It multiplies x minus x1, which is the 1 again. So there it is. That's our tangent line equation. Traditionally, we solve this for y. That's what WebAssign is expecting as well. So let's go through the next steps. We have y minus 2 is negative 3x plus 3. Add 2 to both sides, and y equals negative 3x plus 5. Well, that's pretty much the whole punchline to this thing. We double check our work. Yeah, we got negative 3x plus 5, but it's like twice the amount of work using that definition. So that's the value of the theorems that we've just been going through up above in the notes. They allow all the computations on the derivative side of this process to go extremely fast now. So again, a good takeaway from this is, although we already did this question, these questions do get asked again as we go through chapter 3. And it's always this process now. You don't have to take out the limit definition if you see this type of question again. Well, now that we've gone through it, any questions or comments, folks, on this one? Yeah, go ahead, Andrew.
Yeah, so when is like, do we need to keep practicing the definition? Like, is that going to come up on an exam or anything? Or like on exams, is it okay if we just always solve them this way?
It will come up exactly once. So the way it's going to come up is more like how we saw in, say, 3.2. Or, yeah, 3.2. So this one right here is a potential exam question. It's either going to come up on exam 2 or the final exam, but it's not going to be double jeopardy. If I can't fit it on exam 2, we'll know it's on the final. And if it is on exam 2, it's probably not on the final. And it's going to be something kind of controlled like this one, where the algebra doesn't get too out of hand. And it'll always be very specific. I'll really will print this in bold with yellow, just so as a reminder. This would be the one time where the concept is more what is the core definition of the derivative. But if I don't print those words, I encourage you to do it as fast as possible like we did it here. Always take advantage of the other powerful tools. Does that make sense for that question so far?
Yeah, that's perfect. Thank you.
Yep, you bet. So I guess the takeaway is you'll always have really clear indication if you're breaking it down to first principles like this. I'll always make sure to put that in. In fact, if I forgot, then you're welcome to do this however you'd like. It'd be within the letter of the exam if I didn't put that statement in there. Other questions at all so far? Okay, let's take a look at what we're getting into next. Pretty much the rest of the work in these notes are focusing on just calculating derivatives, looking at old concepts, and then just several problems at the very end of just getting more and more practice with these derivatives. The first, or the second example already, though, looks kind of interesting on its own right. It's saying calculate f prime prime prime. So we're looking at a third order derivative. So this is the third derivative of f. Sometimes when these higher order derivatives get out of control, imagine maybe you're doing a fifth order derivative, the fifth derivative of f. You wouldn't want to put 5 different prime symbols on there. It gets kind of out of control. So sometimes the third order derivative of f, it could be indicated this way. F triple prime at -1 could also be written this way. The parentheses are actually required here. If we don't have parentheses up there, it has a whole different meaning. This is now saying third order derivative, where this is saying a function composition of f with itself 3 different times. Now that's a harder problem in a certain sense. We put the parentheses around it to indicate it's definitely a derivative. Sometimes our author will print it this way. Other times he might go this way, particularly if it's like the fifth derivative or something. So this problem is kind of weird. It gives us a degree 4 polynomial out of nowhere. We want the third derivative at -1, but really the stages to getting through this is you have to walk your way up to the third derivative, starting with the first. So first we differentiate, and going down the line, it's not too bad. Any volunteers for what would happen if we differentiate that first term there? What would be our first term of the derivative?
4x to the third.
Absolutely, thank you. We got 4x cubed on that one. How about another volunteer for next term?
Uh, 12x squared.
Awesome. So we'll get 3 coming down, a -12 x squared. Awesome. We're getting through it pretty quick. Any other volunteers for this one, whether they're in class or in Zoom? Feel free to use your chat as well if you prefer.
38x.
Awesome, thanks, Lauren. So 30x on this one. And honestly, sometimes this one gets a little bit confusing when we're just starting out. Anyone recall what that one should come out as a derivative? Good call. This one is just 3. If the power of x is 1, you just carry in the constant. So plus 3 on this one. Then finally, well, square root of 18 doesn't involve x at all. That one is a constant, so it's 0 in the derivative. So we just don't even write that one in. It could have been extremely awful. Notice how confusing the question could have looked if it looked like that. It just seems foreboding in a certain sense, but same exact response, the derivative would go to 0, and this would be correct. So watch out for weird looking constants. They're really just there to distract you, to see what you'll do with them, it seems like. Well, that was the first derivative, and that was so fun. We'll just redo the whole thing. We're going to the second derivative. We do f double prime of x. But it just means we're differentiating the last line. So same idea. 3 comes down and multiplies. We'll get 12x squared on this one. 2 comes down and multiplies the negative 12. So now it's negative 24. This x turns into x power 1. So we just write it x that way. Now this one's a constant times x power 1. So we just get the constant plus 38. And notice as the derivatives get higher order, the degree is going smaller. That's because this one is an honest polynomial. After a while, if we say took the 5th derivative, the whole thing is just 0. But we're settling down on the 3rd derivative on this thing, so one more step to go. F triple prime of x is going to be, feels like almost deja vu. 2 comes down, multiplies at 12, so 24x on this one. Here, we carry in the constant, negative 24. This term is just a constant term, so nothing happens on that one. And we have f triple prime of x. That means we're almost there. To get f triple prime of negative 1, we just need to throw a negative 1 inside here and get the output. Much like finding the slope on the prior question. So our punchline is the 3rd order derivative of f, oh, I made a mistake there, evaluated at negative 1, not in x, is 24. Negative 1 goes right in this position where x was, minus 24. That's altogether just a negative 48. So that's kind of wild. We've got to that quantity there. The struggle is to interpret it in a physical way. But if you think of this as, say, the position you are away from a starting point, this would be your velocity, like your speedometer in a car. This would be your acceleration. That's the rate of change of your velocity. And this would be what sometimes people call a jerk function. It's the rate of change of acceleration. Having a non-zero jerk function means if this really was a physical ride, say a roller coaster ride or a car, that being not zero means it's probably a really wild one that could possibly need lots of good harness straps to keep you in the seat or something like that. But that's essentially what we calculated going through all this here. Any questions, folks, on the process?
We just work our way down the line.
Exactly. We're carrying it all down to get to that end result. And now what's wild is when we go to integration, we are going backwards, literally. Integration is reversal of all these steps. And that's why in calculus, sometimes knowing this really, really well is what makes or breaks the course, because we eventually have to undo and reverse all of these rules going from differentiation to integration. That's definitely pretty strange. But yeah, just like you said, the process is just go down the line. Other questions or comments at the moment? Okay.
So
Well,
that
next,
-1 on the,
yeah.
oh, sorry. I was just gonna ask, so on the f and then the derivative 3 and then it has a -1, does that not, so if that was like a 5, it wouldn't make any difference to what this was if it was like f derivative 3 and 5?
Oh, you're saying 5 right inside here like this. like that.
Yeah, exactly. It wouldn't make a difference or anything.
It would make just a small change. All we would have to change though is right over here and right over here, we would plug in a 5 and a 5 to get a different value. But all of this right
Oh,
here
okay.
kept the heat of the process completely the same at that stage.
Okay. It's just plugging in for X. Okay. Now I see it now.
Awesome. That's a great question. Thanks for asking about that, Brian. Other questions about that so far? Okay. Well, this next question we're going to take a look at is more important, but it's also a little bit harder. We'll see applications, particularly in chapter 4, but we're going to try to sprinkle in some as we go. So it doesn't feel like we're just smacked with this kind of stuff out of nowhere in chapter 4. So think of this as kind of a preview question, but it's a pretty honest question for this section as well. So what we're doing is some mathematical modeling in this problem. We're talking about, looks like biology this time. Biologists have proposed a cubic polynomial, so cubic because the degree there is 3, to model the length L of an Alaskan rockfish at age A. So more fish modeling, I think we did some of that earlier in the course. Because they're saying it's a model, we're not saying this is exactly the length of the Alaskan rockfish at age A, but we're just saying if you find a random one, this is probably going to be your best educated guess for its length. Here it says L is measured in inches, A is measured in years. So this will give you the length of the fish in inches, and its independent variable is its age, cubed here, squared here, and to the power 1 here. Kind of a strange model. Probably what they did is they took a bunch of statistics, got a scatter plot. I found the scatter plot might have looked something like this. So they're fitting a degree 3 polynomial to it, to real world data. So if you're curious on where did that function even come from, very likely something along those lines. Yeah, these are kind of hard to delete once you put them in. So it says, first, we're going to calculate a derivative, evaluate it at 12, kind of like the last two problems. Include the units as well. Let's put this on a new line. After we do that, we'll give a practical interpretation and answering using the context. To me, this is the major part of the problem. If this was a real exam question, it'd be a little bit less about calculating the derivative, but more of the credit would be given right here on its interpretation. So let's work through this in stages. First, we need a derivative. That's the function, and you could call this L prime if you like, or you could use the notation DLDA. In an applied problem, this notation is a little bit more common, so I'm going to go DLDA to start. And here's a good standard reminder that exams are open calculator. It's pretty much for questions like these. When we take this derivative, 3 has to come down and multiply 0.0155. No reason to work too hard. Let's do this right here. 3 times 0.0155. So our first coefficient is going to be a 0.0465. 0.0465. So that's a 3 coming down and multiplying. That means new power in A is power 2. Then we just do it all over again. We're going to get a negative quantity, so I'll put in the negative just as a reminder for myself. Then double 0.372. Let's go 2 times negative 0.372. We should be getting a negative 0.744. That came from A squared, so now we'll have a power 1 on A, so just A. Next one is a freebie, 3.95. Another freebie, that's constant goes to 0. And so we've calculated half of what was being asked here in a certain sense. We still have to throw 12 inside, but 12 is just going to change the A variable for age. Any questions to this step, folks? Just finding the derivative itself. Okay, and just a reminder for notation, it's completely appropriate and you would get full credit if you wrote out L prime instead. It's more of a stylistic choice to use DLDA. It also helps with this with units, so it's a pretty interesting notational device, even though it's really clunky. But now let's do this portion, evaluating when A is 12. So DL, DA, I think this is a good point to start adding some colors to this. We're curious when A is 12 on it, so set this to 12. Now all we're doing is plugging in 12 in the equation above. So let me write it in as 0.0465. Put in a blank to power 2 for 12 in this location. Then same idea here, negative 0.744. Multiplies that 12. And then we add 3.95. Okay, so there's our derivative. Next thing to do is just to jam it into the calculator. So 0.0465 by 12 squared minus 0.744 times 12 was 3.95. Let me see if we've got that all in there. Okay, so I've got a 1.718. That look about right to folks so far? Okay, let's throw that in, 1.718. Now that we've gotten that, this thing is really easy to miss. Some of the problems do ask for units. It's always going to be an applied problem like this one, and it's usually because we're doing a little bit more. We actually need the units to get a decent practical interpretation. And there's a really good trick to this. Let's color code it even further. We had a variable A, and we know A is in years. We also have a variable L, and we were told L was in inches. So coming back here, the units will always match the units in the numerator. You can say inches per, or if you want to match with a fraction, you can do that as well. In the denominator of that fraction would always be the units of the denominator in this Leibniz notation. It's not quite right to call it numerator denominator. It's not even really a fraction. It's a limit as h goes to 0 of the difference quotient, but it's not a bad thought. Take the numerator here, denominator there, just match up units. So that's what it looks like all together, putting things in. So we've done this portion. Now we just need to interpret 1.718 inches per year. One way to think about that is the analogy of driving a car is always a really great one. When you're looking at your car, you're looking at, say, miles per hour. It's the same kind of interpretation, but your miles per hour depended on an instant of time. Here, the 1.718 inches per year depended on the fish was 12 years old. It's not going to grow that fast at 0 years old, for example, when it's like a couple days old. That would be crazy. So this also depends on time. It's going to change as the age changes as well. So finally, for the practical interpretation, we'll say when the Alaskan rockfish, we have to convey this right here because we have to say what the problem is all about. And that's what this is saying, using the context of the problem. We have to return to the original things we were studying in the first place. So we can begin by saying when the Alaskan rockfish is, first foremost, we want to talk about the instant of time this derivative occurred. So we'll say 12 years old. Now, if this was negative, we would have said it's decreasing, but that would be kind of weird for this model. Because that's a positive quantity, we're going to say is growing rather than shrinking. It's growing at a rate of the 1.718 inches per year. So finally, that's the full statement right here. If this model is accurate, then if you have a 12-year-old Alaskan rockfish pet for some reason, you can anticipate it's growing that fast at that instant of time, right when it turns 12 years old. When it's 12 and a half years old, this does change. because it changes at every instant of time. Well, any questions at all, folks, on running through this kind of a preview question so far?
The bottom here.
Exactly, yeah. Well, I think that's a good thing to indicate right here. This down below is the practical interpretation. There we go. I think that's a good emphasis to add here to the notes. Any other questions or comments, folks, getting through this problem? Okay, it's definitely kind of a weird process, and this is really our first example along these lines, dealing with an application and trying to interpret a quantity. We'll practice this quite a bit as we go through the notes, and by the time we're doing this in chapter 4, when it becomes more of a typical exam question, it won't be something that's coming out of the blue. That's pretty much why we're sprinkling it in the notes here and there as we go through. Well, let's take a look at what we're getting into very next. After these first 3 examples, pretty much the rest of the work is we're just going to practice dealing with some derivatives. But the next section is pretty pivotal. I put some notes here in yellow, and these are common issues that occur in this course whenever you're learning calculus for the first time. It says here, look before you leap. Some of the functions need to be simplified. That's one that absolutely does need to be simplified, because you'll notice up in the formulas, we never stated a formula for when functions are multiplied and they involve x. The only time we stated a formula is when a constant multiplies a function. That we can handle, but this requires a new formula. Now, this is where a danger occurs. It's a good idea to pause right here and mention it. If you use the formulas that are in just the very next section for the product of a function in this context, you're making the problem a lot harder than it actually had to be. So part of the rules that we're going to see up in this next section, 3.4, part of the main issues with these rules, doing the product of a function, is knowing when you actually want to use it. You should definitely not use the product rule in this case, and it's an easy thing to forget once we get further on the course. I mean, especially after you just study the product rules, you probably would want to. But actually, it's way easier to just FOIL that out and differentiate like we're doing in section 3.3 in these notes. This is the function where you have to use the product rule. There is no way to simplify this to get a sum inside there like we could over here. You could just break that up. But this is a product no matter what you do. That's the one you use product rule on for sure. We'll talk about those issues more and more as we get through the course. But for the moment, in section 3.3, the takeaway is you can't calculate the derivative of this one independently, nor this one, nor this one. We actually need to do something algebraically to break this up so that all of our prior rules still work. Well, let's give this a try. First one's kind of a refresh in a certain sense. There's nothing too crazy going on. We could say y prime to start. And here's how the process goes. This is a power function, x to a power, so 4 multiplies 6, giving us a negative 24. And x will be to power 1 less, so power 3. Then it's rinse and repeat. This will be plus just a 6x on this one. So the 2 multiplied to 3, giving us a 6. X dropped down to power 1, and we just typically leave it like that. This one's kind of dangerous, though. Anyone recall what should go right here, if anything? Yeah, go ahead.
Would nothing go there because it is, I did the rule, but E doesn't go to just 0.
Exactly. This one's really just a cleverly disguised constant, right? We have to know that if you're looking at that, there are no x's there, and just like you said, this one goes to 0. And, you know, having a calculator on exam is sometimes kind of a help on that. You could just go and put in your E button is usually under the logarithm key, and e to the power 4. It's about 55 if you're rounding. So that's just a weird way to write something about equal to 55. In the end of the day, it's just constant, so nothing goes there. But notice that 4, what it's trying to do is to see if we're going to use a product rule by making the 4 come down, put 1 less. All of that's just a pure distraction. We have to know to ignore that And that's our answer. Well, part A is kind of a nice one, other than the trick question on the very end. But part B is kind of the nasty one we're talking about. This is one where you definitely would want to look before you leap and start simplifying things down. So half the work on this, maybe even more than half, is just pure algebra. For me, I think it's a good idea to just FOIL these out first. Then we'll distribute the root of x into that result. So let's begin by saying f of x equals. Let's put down some formulas as well as we go. What's kind of interesting about where we're at right now is we're kind of doing two things. We're doing calculus, and we are absolutely refreshing our knowledge on exponential notation because it comes up in a huge way all of a sudden. If you see square root of x, that's just x to the power 1/2, but we'll have to use and abuse that fact. And if you ever take, say, x to the power m, multiplying x to the power n, in this arrangement, exponents add up. This will be m plus n. But it doesn't matter if they're fractions or integers, or just any arbitrary real number, that law always follows. So now back over here, we can call root x to the power of 1/2. Next, we're FOILing out 4x minus 3 times x minus 3. Here to here will give us the 4x squared. And here to here will give us negative 12x. Let's carry over to, now the negative 3 distributes in, here to here for a negative 3x. And here to here for a plus 9. We still have to add up the stuff in the middle, but we're getting through it now. So keep on following the equalities. This is still f of x coming down. Let me fix this pen so that red dot doesn't keep bouncing around. Power of x is still 1/2, and we have, here it's 4x squared, but we're going to use this formula where we're adding exponents. A better way to write power 2 is x to the power of now 4/2. Reason for that, x is going to multiply this, and it's going to bump it up to power 5/2 when we add up the exponents here and here through that formula on the right. So now let's start to fix more of these. Negative 12x minus 3x gives us negative 15x. It's power 1 right there, so let's write it as power 2/2. And then plus 9. So now that we're here, we're still are not in a good shape to use any of our formulas. It's all because of the multiplication there. We need to eliminate that. So now x distributes into the group. And here's how it goes. When it's here to here, we carry in 4, x to the power of 4/2 plus 1/2. It's now to the power of 5/2. Then rinse and repeat. X is going to multiply here next, so that's negative 15. It was power 2/2, but add 1/2, and we get 3/2 altogether. So x to the power of 3/2 plus 9. Now, the supplied function, this one, is in about the worst format you would ever want if you're differentiating a function like that. That's the format you want. It looks a little bit uglier, but now our power rule works, our sum and difference rule works. Everything can go as planned. So now we're at the stage where we're about to calculate the derivative. Let's restate this formula just for completeness, or just to make sure it's available. This is just the ordinary power rule. The important feature of this power rule is that exponent n can be any real number whatsoever. It could be a fraction, it could be pi. It always works in this format. So if it is a fraction, it just looks awkward, but it's business as normal for this function. Here's f of x. Next line is f prime of x. And here's how we're going to go step by step. First, constant multiple rule. Let's be careful with this one and just carry in the constant this time. It'll multiply 5/2, so 5/2 just copies down. And here's the tricky part. Any volunteers for the new power on x? Exactly. It's always going down by 1, no matter what. It just so happens it's annoying this time, right? It's 5/2. -1 is what we're doing for the exponent right here. That means you can think of it as a 5/2 minus 2/2, giving you the 3/2. So that's going to be our new exponent from here down to here. The way people typically visualize it, rather than writing it down, this is more for the notes as a paper trail. You can think of it this way. If the denominator is 2, you're just subtracting 2/2 from this. So power is 3/2 altogether. Then rinse and repeat. First, any questions, folks, on getting through that first term? Okay, I'd say a good takeaway with this one is it shouldn't feel like we're doing anything fundamentally different from, like, say, these kinds of derivatives. It just so happens that now we're focusing on nasty exponents just to see what we have to do algebraically to survive them. So on the next one, let's carry down -15 to start. Let me put in some extra space. Then we're going to multiply by that exponent just as it is, so times 3/2. Then x goes down by 1, but the denominator is 2, so we subtract 2/2. New exponent is 1/2. And because 1/2 occurred, you could put in square root of x if you like. To me, I consider that a stylistic choice. If you leave it as a fractional exponent, I'm completely fine with that as well. So I'm not worried about fraction exponents, negative exponents. As long as your answer is simplified, you're in good shape. So the only thing we have left to do is to simplify these multiplications here and here. That's because the constant went to 0 and we're done with the derivative so far. Any questions at all, folks, to that stage? Okay, really not much to do. I mean, 2 divides here, leaving this a 2/5. So this is 10. X to the power 3/2. Here, I would just multiply across the numerators, divide by 2. So this one's -45 halves. And I probably would leave this as x to the power 1/2. I'd only convert it to square root of x if there was a really good reason to do that. Taking those extra steps just to make it look pretty, I don't know if there's any real value to that all the time. But if you're looking at the back of the book, that would probably be the one time. Well, any questions at all, folks, on getting through this part B right here? Okay, so the takeaway on this one is it really goes back to this statement right here. Looking before you leap is making sure your function is even in the right form to differentiate it. If a bunch of things are being multiplied or divided, you need to do some algebra to make them look more like, say, this right here. Those are the things we're meant to differentiate in this section. So let's keep on going. Let's see what else we have going on. Part C is weird because it's fast, but it's kind of issues dealing with what we've seen before on doing the derivative on this one coming down here. It says y is t to the power of -2/5. So y prime. It's fast, but it can be tricky. We just have to be careful with it. First thing that will always happen is that -2/5 becomes a coefficient. The variable is t. I'm not picky if you change this to x on your work, but WebAssign would be picky. You have to keep it at t if that's how it was indicated. Now the power was -2/5. Any volunteers for what the new power should be then? How about for someone in Zoom? Any volunteers for what the new exponent should be after that -2/5 come down? Oh, sorry, go ahead. Yeah.
Negatives.
Exactly, yes. I think we had a tie in class and over Zoom. It should be -7/5 altogether. Again, it's kind of like looking at the denominator. If you have a denominator of 5, you're just subtracting 5/5. In essence, you're just subtracting 5 from the -2, so -7/5 altogether. This kind of work you could always do in the margin, but I think it's faster to just look to the denominator and subtract in that way. So the moment you put -7/5, all the work is done with this one. That is the answer right at that stage. It just feels funny dealing with the fractions, but once we get used to it, it's kind of becomes business as normal with these new derivatives. Which one that is kind of new is this one right here. Now, I do have a lot to say about this one. There's a common error that does occur in a calculus course where if you're differentiating something like this, your thought might be, I cannot use this formula. And you are right, this formula does not apply. Let me restate it down here so it's just visible. Here's the power rule once again. It's pretty much one of our big formulas for differentiating. But one thing this power rule insists upon is that x is not in a denominator. Here, the variable s is in a denominator, so we have to fix that. Here's the second danger that occurs. In the next section, we're going to have something called the quotient rule. But there are times where you absolutely do not want to use the quotient rule. It's even more convoluted than the product rule. You can take a small problem like this one or this one and make a mountain out of it. You really wouldn't want to do that in an exam setting in particular. So that's the warning on this one. It really still is the power rule, it just doesn't look like it. Like in the last problems, we just have to do some exponent surgery on it to get it into the right format. And here's the exponent law we need. If you ever have something like this, 1 over x to the power of n, that's not great for us because this formula doesn't work, but you can fix it. You can bump x into the numerator and the exponent is now negative n. In other words, if you change positions from denominator to numerator, you're changing the signs of the exponent and vice versa. If you go from the numerator to a denominator, a negative n becomes a positive n. So we can go to all three of these denominators and just fix them as we go. Let me make that a little bit bigger so we can see all the features there. So this will turn into negative 3 times s power negative 4, for example. So in this format, really bad for differentiating. You definitely don't want to use a quotient rule. You'd have to use it 3 times and the problem goes insane on us. Instead, just go like this. A of s, whatever a is and s is, becomes, on this first term, negative 3, s power negative 4. This one is 9 times s power negative 3. And this one is convoluted. This one needs its own discussion. So let's do this one on the margin as a own decent problem on its own right. Let's see how to correct that one. So if you see this kind of stuff, here's the idea we need from exponent laws. The mth root of x to the power of n is the same thing as x to the power of n over m. Actually, I want to change the coloration of this just a little bit. So mth root, n over m like that. In other words, the big takeaway for this is, if you're going from radical notation, like what we have up here, but you need exponent notation because you're differentiating through this formula, you take the index of the root and put it in the denominator, and you're all set. The numerator power just came from what was already here for x. So likewise, if we use that process on this portion right here, highlighted in green, here's how it would go. It starts off as 1 over 5th root of t cubed. That 5th root, however, becomes the denominator where we see the t cubed, and so it turns into 1 over t to the power of 3/5. Then once it's in this format, it's still not ready to go. We need to take that base t, bump it up to the numerator, which means we're negating the exponent. It's now negative 3/5. And so that's the correction of this one. 1 over 5th root of t cubed is just being rude. That's hard to differentiate. If you ever see that kind of question, then it's more about just knowing the exponent laws and knowing to correct it to this position. It should be t power negative 3/5, because now this rule right here is in effect. Any questions at all, folks, on that exponent surgery right here? Or any of them, rather? Okay, if we're happy with this, then the good news is we're pretty much done then. We are going to go left to right, term by term, just nail all derivatives simultaneously. So you can either go a prime of s if you're in prime notation. If you like Leibniz notation, you might call it dA ds, but whatever you call it, you're really just doing the same thing. You'd only have to write one of these. So whichever you prefer. -4 is going to come down, multiply the -3. So it's 12 s to the power of 1 less. So that will go down to a -5. Same game on this one. This is -3 times 9, so -27. S to the power of -4. And this one looks like it's a trick question all of a sudden, out of nowhere. That one is constant with respect to differentiation with respect to s. Nothing carries down at this stage. And that is really weird. That's the new element on part D. Let's put down a comment here. Goes to 0. Let me maybe do it slightly better this way. There we go. That portion goes to 0 since the independent variable we know to be s. I'll just say is s, because the function was indicated to be s for the independent variable in function notation. Now, if you differentiate something that involves a new variable, that is also constant with respect to the differentiation process. We consider a fifth root of t cubed constant if you're differentiating with respect to s. It's kind of a surprise, and again, that's the value of this notation right here. It tells you anything involving the variable t is just gone. Does that make sense to folks with that idea so far? Okay, so it's kind of tragic in a way. We did all that work to come to here and we can't differentiate it. If you did differentiate it, here's how it would turn out. The derivative with respect to t, not s, of t to the power of -3/5 would be -3/5. Subtract 5/5, so it's now to a power of -8/5 on that one. So if that was written with the variable s, that's essentially what we would have put in with the variable s right there. But kind of a trick question right out of nowhere. Any questions or comments about that so far, folks? Okay, as you go through this document, you'll notice every one of these problems has one strange issue. I double-checked the homework. I actually did, in fact, double-check it. For every one of those problems in there, some of them look strange, but you can scroll through and find something that's familiar. So if you see something like this is terrible for us. You might decide, hey, there is a quotient rule. You can use this process. That's even more terrible. You would be working harder than you have to. What you really want to do with this one is just simplify it just like before. So we're going to begin by taking root x, that's x power a half, divide it into everything, and then just differentiate the result. So if you have things multiplied together, distribute through, FOIL them through. In this section, if things are being divided, you just need to literally divide it into your numerator and you're all set. And that says f of v. Let's correct that to make it be an x. So this turns into a sensible problem. Sorry for the last minute correction on there. This one was revised to x. Without that x there, f prime of v would have just been 0. There is no v whatsoever in that process. But now with that new correction, f of x is equal to, that root x is going to be an x power 1/2. So let me write it in just once. I'm thinking of that root x dividing into x squared. That means we should correct the exponent on x. X power 2 is the same as 4/2. So now we have compatible denominators with the exponents. Then we just do it all over again. This is 4x from that red dot. It's still being divided by root x. We're writing it in as x power 1/2. That looks kind of funny. Let me make sure that actually looks like a fraction. X power 1/2. So up here where it's x power 1, just put in a 2/2. The last one is nothing special. It'll just be -1 divide by x power 1/2. We'll correct this exponent by making the 1/2 negative, bringing the base to the numerator. But for these others two, that's just a brand new exponent law. It goes like this. If you have x to a power m divide by x to a power n, instead of adding the exponents, we'll just subtract them. So this will turn into x to the power of m minus n. So that's pretty much all we're doing here. It'll be 4/2 minus the 1/2. So on the very first term, we'll have f of x equals x to the power of 3/2 to start. So we're really just subtracting from denominator into the numerator. Likewise here, it's 2/2 minus 1/2. So this will be +4. X power 1/2 on this one. And this one's a completely different trick. We're going to take the base, put it up into the numerator. So it'll be negative x power -1/2 because of that switch. So finally, this function is a terrible exam question. And the reason we're harping on this so much that you definitely do not want to use the quotient rule on certain things like this one as well, is because when these questions come back, say on a final exam, they go from being not bad in this section to suddenly really tough questions because we know about the quotient rule. Knowing the quotient rule is not enough. We have to know when to use a quotient rule. So we'll focus on that as well in section 3.4. But now that we've taken a quotient, written it in this way, we're just going to use the good old power rule repeatedly. So we're essentially there. You can write f prime of x equals, on the first one, 3/2 comes down, and it'll be x to the power of 1/2. We subtracted 2/2 on that one. Here, you can make a choice. It's going to be f times 1/2. If you write that in here, we have an extra step to simplify. But if you know you're just taking this times this, and you wrote in a 2, that's a good shortcut to take, I'd say. It becomes more familiar the more we differentiate. So I encourage you to take that if it makes sense. For us, we're just looking at these things for the very first time, so I'll take the additional step in the notes. It's +4 times, now we're differentiating, 1/2 comes in. Any volunteers for what the new power should turn into from here to here? Yeah. It wouldn't be a 1/4 right here. We would have to subtract a 1 from this altogether. Anyone see what it should be?
-1/2.
Good call. This one turns into -1/2 altogether. I mean, this one feels weird because we're going from a positive to a negative exponent altogether. But same idea applies. Whatever that exponent is, subtract 1. Because it's a denominator of 2, we're subtracting 2/2. So it's like we're taking 1 minus 2 for -1/2 altogether on that one. Then one more time. -1/2 comes down and multiplies this negative, so it turns into +1/2. I'll write that in as an additional step. Up here, subtract 2/2, so this will turn into a -3/2. Although it's not a lot of credit, if we wrote it out this way, we still have to simplify. So we'll divide here, flip the negative signs, and this is our end answer. Copying, we have 3/2, x power 1/2. Here it's going to be +2 x power -1/2. And from here, +1/2, x to the power -3/2. Looks like we got it, folks. That's the full derivative of that nasty thing. Again, they're not bad problems as they stand, but when you get more material, more formulas for differentiating, this one becomes outrageously tricky just out of nowhere. But any questions, folks, on getting through it with this method? Okay, I'd say at this stage of the notes, we got through kind of the main questions we want to get through. I have a couple more that are just slightly interesting in their own way. Like say this one, for example, e to the power w plus 1 plus w. Let's pull in some formulas we need for this one. First thing to note is the independent variable, which is typically x, is now a w. And that means this is a natural exponent function. But it's also a function composition because there's a +1 inside there. That is problematic for us because we know our formula goes like this. Derivative with respect to x of e to the x is itself e to the x. Now, if you change what goes up here, it can sometimes, in fact, change the result over here as well. E to the power w plus 1 isn't anything major, but if there was like a 5 right here, that is major, and this formula is completely invalid all of a sudden. As it stands, the formula doesn't even work like this. We have to show that it can work. But once we discover it works, we'll be in good shape for doing more problems like this one. So first thing we'd want to do on this is, let's take e to the w plus 1 and factor it. That's a weird thing to say, but it truly does factor. You could write this in as e to the power of w times e to the power 1. That works because they are the same base. You just add up the exponents, w plus 1. And you can reformat it as e times e to the power w. So that's probably what you'd want to do first thing on this one. Z turns into a new function that's e. That's just a coefficient, a weird one, times e power w. And the whole reason for doing that is we can now use this formula just as it's stated. So now we'll go plus w, and we can differentiate it at this term, at this stage. So this is one of those rare situations where to get started on this one, algebraic method was the factoring, but a weird kind of factoring. We're just breaking up the power, essentially. Now, when we differentiate, you can call this one a z prime if you like, or if you prefer, it could be a dz, dw would be just as fine. I'll go with Newton's prime notation on this one. But in differentiating, that is considered a constant now. So constant multiple rule says e is copied. Next, the natural exponent law says derivative of e power w is itself, so it goes in. This is the derivative of like x to a power 1. The derivative of a simple variable to the 1th power becomes 1 altogether. I feel like this one is kind of tricky. Does that make sense to folks going there to there? Awesome. So if you feel good about that one, we're in good shape then. Any questions at all, folks, getting to that end answer then? Okay. One thing you can say, if you decide to simplify your answer a little bit more, the result of this derivative, z prime, is e to the, notice you can now just multiply them together. It's back to e to the w plus 1. Plus 1. So it does look as though this derivative carried down in the way we'd sort of expect by the formula for the natural exponent. But that's a dangerous assumption because we're going to find out later that if you differentiate this one, let's call it e to the 2x, this one is fundamentally different than, say, e to the x plus 1. This requires something called the chain rule. We'll investigate this later on to see how it goes, but eventually becomes this, e to the 2x multiplied by the derivative of 2x is what the chain rule is going to give us. We differentiate the outer function, which was the exponential. Then we differentiate the inner function like this to get e to the 2x times 2. So the derivative here is not just e to the 2x. There's a real change that occurs. And that's why we're so careful and paranoid when we see e to the power w plus 1, because that's not how our formula was stated. It's a coincidence it worked out, in other words, for this problem. But I would say this is just a preview really for us. And it's a reminder of why we have to be super careful even on this problem, even if we anticipate it should have worked out like that. Phew. But after getting through all that, we have one last trick question. If y is 3 times e to the power of 8, any volunteers to shout out the derivative for that y? Good call. That one is just 0 because that's just a really weird constant. Pretty large number, but it's 0 altogether. Let's just put emphasis here for our last problem, constant. These deserve exclamation marks because it's not always easy to spot a constant. The moment you do spot one, that's wonderful. You don't work very hard to find its derivative. Well, folks, that's a rundown of all these different differentiation formulas and such. Any questions or comments at the moment? Okay, so that's the wild world of derivatives. I mentioned before, some of these derivatives are more nasty than they really look, not because you're in section 3.3, but it's because you're in section 3.4. We're going to delve into this quite deeply when we come back on Wednesday of next week. And our major things that we're going to worry about is these kinds of functions should never involve the quotient rule. And the reason is on this one, this function should be thought of as x over x plus 1 over x. This x over x right here would turn into a 1. The 1 over x, definitely don't use the quotient rule on that one either. That's just x power negative 1. So now if we differentiate this thing, on the very first term right here, that's a constant, so it's just gone. Here, negative 1 comes down. New power is 1 less, so it's power negative 2. If you use the quotient rule on this one and compare solutions, you'll notice quotient rule, even though it's powerful, it causes more harm than good on certain problems. So we'll try to always focus on that whenever we're using quotient rule, product rule. This one is not so nice. You can't just divide x plus 1 and break things up in this way. That one really requires quotient rule. Those would be problems where we'd have to use it on. Well, I think that's a good stopping point for us, folks. The last extra minute and a half is kind of stretching it. Any other last questions then before we call it a night? Okay, this will be our stopping point then. And just as a reminder, through requests and inquiries through the class, we are going to cancel our night class on the 14th since it's Valentine's Day. That'll be our catch-up day. So if you're a little bit behind a web assign and you're working, I'll be working too. Don't hesitate to hit the Ask My Teacher button, email me, things like that. I'll still have ordinary office hours. Then the 19th is President's Day right after that. So we'll be returning to these notes on the 21st. Well, have a great weekend, folks. Oh, sorry, last question.
Quiz 4 anytime.
Yeah, absolutely. Quiz 4 can be handed in at any point. Absolutely. Other questions at the moment? Okay, well, have a great night, folks, in class and over Zoom. If questions come up, don't hesitate to ask. Otherwise, I'll see you on, geez, that's a while, the 21st.
And if we have any questions.
Absolutely, yeah. I'll be available all throughout as well.